This is Professor Coles. I'm going to give a short presentation on Froude's resistance decomposition method and model scaling procedure, which we've discussed a bit in class, but I'll try to give an overview here. It's mostly historical context. It was this first sort of approach of being able to take the resistance of a model measured in a tow tank and be able to use that to estimate the full-scale drag on the drag on a full-scale ship. There have been some improvements to the method following the work of Prandtl on boundary layers and the work of Kelvin on waves, which sort of followed Froude's work, so the fundamentals of those fluid mechanics were better understood, and then the model testing approach was refined over the years. And I'll discuss the more modern approach in the follow-up lecture, but the basic concept is the same. The details are a little bit different. So we start from just sort of reviewing the resistance components we've been looking at. If we have, so here's the center line of a ship, and looking from above, we've been focusing on three resistance components. One is the wave making, so the ship makes a wake, which we examine as the Kelvin wake with that divergent and the transverse wave structure. And in order to generate, in the process of generating waves and then continuously transferring energy to waves, there's a drag associated with that. The drag manifests itself in the pressure distributed over the hull. The second component that we looked at, so that's wave drag. The second component is the friction drag. The boats are typically high Reynolds number vehicles, so there is a boundary layer, but confines itself to a pretty thin region very close to the hull, where the viscous effects are important. So, but even though it's a thin region, there are large shear stresses associated with that boundary layer, which manifests themselves in a parasitic or a frictional drag on the hull, in opposing the direction of travel within that boundary layer. The third component of drag is what we've been referring to as viscous pressure or form drag. These boats in general don't tend to be super streamlined. They have to be beamy for stability and carry a lot of volume aft in order to have good seaworthiness and carry a lot of cargo. And for that reason, the streamlines don't tend to close smoothly around the stern. There tends to be separation, even in the presence of high Reynolds number flow, a small separated region in the stern, and that's a drag that manifests itself in the pressure distribution. So you don't have full pressure recovery of the streamlines, and you have a lower pressure than you would if you had full pressure recovery. And this is a drag, a form drag or viscous drag. So there are three components: friction, viscous, and form drag. If we look at that total resistance, we can write this as RT, total resistance, is the friction drag plus the wave drag plus the form drag, which I'll call R form. If we divide this, all these three, by 1/2 rho v squared s, where s is the wetted area of the hull, I have non-dimensional forms for all these. So I have CT equals CF plus CW plus C form. Now the assumptions of Froude were how these scaled with the critical non-dimensional parameters. Fundamentally, the ship drag problem depends on a lot of non-dimensional parameters, but most of them are negligible. For example, the Mach number is certainly negligible. The Weber number related to cavitation is negligible. For most ship problems, that's nice. The cavitation is negligible. So we're going to ignore those and maintain, apologize for that, maintain the two critical numbers. So CT is going to be CT of Reynolds Froude. CT of Reynolds and Froude. So those are the key numbers. Of course, as we learned in class, To have full dynamic similarity, the model would have to carry the same Reynolds and froude numbers. If that were to be the case, then the measured drag coefficient of the model would be the same as full scale, and you'd be able to compute directly the total resistance in newtons on the full scale. But you can't match Reynolds and froude, so we choose to match froude. The assumptions of the resistance decomposition are that these pieces up here, these components up here, can be broken down in the sense that we can write this as CT equals CF as a function of Reynolds number, and we'll talk about these assumptions in a second, plus CW as a function of froude number, plus C form. So in the froude approach, and this is the most difficult one really to get at, this form drag, how to deal with viscous pressure resistance. In the froude approach, we're going to assume that C form is a constant. It depends only on the hull, and if the hulls are geosimilar, as the model and full scale should be, then that form drag coefficient is a constant, and it is the same for both model and full scale. That's in the froude approach. Later we'll look at a more an approach which tries to tie that into the physics a bit better. So this assumption here is that the friction depends only on the Reynolds number and the wave drag only on the froude number. And certainly the friction does depend strongly on the Reynolds number, but we're missing some interaction between these components. For example, the wave making itself will generate waves along the hull, which varies the pressure distribution along the hull as a function of froude number. Remember that transverse wave train wavelength is a function of froude number, so where the waves are acting along the hull will vary with froude number, and that pressure distribution will modify and interact with the boundary layer. We're assuming that there's no interaction in this case, that the variation of froude number at a fixed Reynolds number will not affect skin friction, CF. The same with the wave drag. The presence of the boundary layer and a thicker or thinner boundary layer, depending on the Reynolds number, will also influence the wave making, but we're ignoring that because these effects are small. So we split it up in this manner. CF a Reynolds number, CW froude number. Now the model froude number, we're going to make froude's assumption. We're going to test them both the same froude number. So model froude is equal to full scale froude, where I'm using the subscript M for model and S for full scale, or the ship. So this establishes the regime that we're towing in. The model will be towed at a smaller Reynolds number by nature of its slower speed and smaller length scale. So it will in fact have a different skin friction coefficient CF. In general, it will be a larger skin friction coefficient because CF decreases with increasing Reynolds number. So the full scale ship will have a smaller CF than the model will. But that's just a skin friction coefficient. Now what we can do is we can group these two terms together. We're going to define a new resistance called residuary drag. CR equals CW of froude plus C form. Now the CR is dependent on the froude number and only on the froude number. It's a froude number dependency and a constant dependency. It's called residuary drag because it's the result of taking the total drag. It is equal to this total drag minus the friction drag. So the difference between the total drag and the friction drag has to be these two other components, the wave and the form drag. So it's the residuary, meaning the residual. The residual is what's left over after you do the subtraction. CT minus CF. So let's go and start thinking about computing. How are we going to get the full scale total resistance coefficient? So what does that look like? CTS is equal to C, the friction on the full scale, which is a function of the Reynolds number of the full scale, plus the wave drag of the full scale, which is a function of the froude number, which is the same for both, plus the form drag. I'm running out of room here. But these last two together are the residuary drag. And since they're the residuary drag, and we can see here the residuary drag, actually let's look at this equation here. The residuary drag is the wave drag plus the form drag, depends only on the froude number. that means that the residuary drag for both model and full scale are the same because it depends on froude number and a constant, which we assume to be the same for both, for the function of the hull shape, which is the same for both model and full scale. So we have this thing in parentheses we can estimate directly from the model. That is equal to, up here, where did I put it? We have this residuary drag is equal to the total minus the frictional. And we can compute the total drag on the model, and we can estimate the frictional drag on the model, which can get us to the residuary drag here. So I'm going to say CTS is equal to the friction drag on the full ship, which is a function of the Reynolds number of the full ship, plus CR, the residual drag, which is the same for both model and full scale. And in the model, it's equal to the difference between the total drag coefficient and the frictional drag coefficient. So this is going to be equal to CFS, which is a function of the Reynolds number of the ship, plus this difference, total drag coefficient on the model minus the frictional drag coefficient on the model, which is a function of the Reynolds number of the model. We can reorganize this. The total drag on the ship is equal to CTM, let me move that over to the left, minus the difference between the frictional drag on the model, which depends on the Reynolds number of the model, minus the frictional drag on the full-scale ship. So there you have it. So the idea is as follows. First, you compute the total resistance of the model using, apologize for these stupid things, using, where's my, using the resistance, calculate the resistance of the model in the tank and non-dimensionalize it, and there's your model with total resistance coefficient. We calculate the skin friction of the model using a skin friction law, and we'll talk about the ones that are standardized now, but in class we've been using the 1/5 power law, the turbulent 1/5 power law, which is a function of the Reynolds number of the model, function of the Reynolds number of the ship. In general, CFM will be larger than CFS, so this thing in brackets will be positive. So the total resistance coefficient of the ship will be the total resistance coefficient of the model minus some positive number. So it'll be less than the total resistance coefficient of the model. So we have a process now by which we can get the total resistance of the ship. Given a tow tank measurement for the total resistance of the model and estimates of the friction on the model and friction of the ship, the coefficients, we can get to the total drag on the ship, the drag coefficient, which could be converted to a drag in newtons. Now this relies on this assumption that the friction drag depends only on Reynolds number, that the form drag is considered to be constant, and that the wave drag is a function only of the froude number. Those assumptions are inherent in our ability to be able to do this. Now what does this look like graphically? Draw a little axes here. Okay, let me clean this up. Try this again. Okay, so the x-axis is going to be Reynolds number. The y-axis is going to be any of these coefficients, CT, CF, CR, etc. If I draw a friction line, it might look something like this. We see it sort of decreasing with Reynolds number. That could be any one of the friction lines, and they're all similar. They're all fairly similar. When you plot them on top of each other, they tend to stray apart at very high and very low Reynolds number, but the middles are pretty close. So the idea is the model. The model's tested at a lower Reynolds number. So let's say it's here. The model's here at this Reynolds number. And we compute the total drag coefficient. Now it'll be more than the frictional drag because the total drag should be more than the frictional drag. We'll put it up here. There's the frictional drag. I'm sorry, there's the total drag of the model. Total drag coefficient of the model up there. this part we can estimate right here. This is the frictional drag. That's a function of Reynolds number, frictional drag coefficient. That means whatever's left over, the distance from this friction curve to the total drag, which was measured in the tank, is going to be the residual drag of the model, CFM. The residual drag includes the wave and viscous pressure components, or form components, neither of which are easy to estimate. So we measure the total, we subtract out the friction, we're left with what's left, which is CRM. Then we come down here. Let's say the Reynolds number of the full-scale ship is over here. It's going to be higher. The friction coefficient will be smaller, but we can estimate it using this drag curve. Now we want to get up to the total drag of that ship. But our assumption is that this residual drag is the same. So I take this chunk, whatever it is, and I move it over here. So that the length of that red line is the same here and here. It's supposed to be the same. I just moved it over here, add that onto the friction drag, and I get my total resistance coefficient, CTS, of the ship. And here's CTM that was measured of the model. So that's basically the process, and that's set up in these equations. You can look at it. You can write it either way. You can write it as the friction of the ship plus this residuary drag, or you can write it as the total drag coefficient on the model plus the difference in friction drags. It's this equivalent thing. You can think of it graphically here. We're measuring this. We subtract out friction, leaving CRM. CRM's the same as CRF, which is right here. So we add CRF onto CFS to get CTS, and you're done. So that's what's happening graphically. You can see in this chart, and because the frictional curve is dropping with Reynolds number, the friction is going to be less on the full scale, the coefficient of friction. So the total drag coefficient will also fall. Now, in a later lecture, we'll be discussing systematic series. Sometimes systematic series report this, the drag coefficient on the model. Sometimes they have already subtracted the friction for you, and they report the residuary drag. But you have to be a little careful. You have to know how they subtracted the friction, because there's different estimates of friction. You want to know what that is. So there isn't really a standard for reporting results of systematic series, and over the years that has kind of changed. And so we'll evaluate a few different systematic series, and you'll see, and the book explains in very good detail how you're supposed to, what data is presented and how you would use that data to reconstruct the total drag of a ship that's based on the model that you're examining. So this residuary drag will come back. That's basically Froude's hypothesis, or Froude's resistance decomposition method, and model scaling procedure in a nutshell. As I mentioned, there's been some refinements to this, and we're going to discuss that in the next short lecture. It's just a slight modification, really, on this procedure that tries to bring in a better estimate or better physical fundamentals of that form drag coefficient, namely not allow it to be constant but vary with Reynolds number. This will bring in a new coefficient, K, which is the form factor. So we're going to bring in a new unknown that we sort of have to get at, but we'll get at that in the next lecture.